Hi everybody, welcome back to our astronomy discussions. We've so far gotten through Unit 3 about light and matter, talking about just characteristics of light and some characteristics of matter, and then in the last video we introduced blackbody radiation and explained how astronomers can use starlight to determine the temperature of a star using a relatively simple formula. In this video, we are going to discuss other features of the spectrum of a star. The spectrum, again, being what you get when you use some sort of device like either a prism or a diffraction grating to break the star's light apart into its component wavelengths. So this right here is a picture of an absorption line spectrum, where you see what would ordinarily be a rainbow, but with lots of features on it. Here is another more precise picture of such a thing. In fact, this is the spectrum of our sun. So the question is, why are all of these dark lines there? And can you have the opposite of dark lines? Can you have bright lines on a spectrum? The answer is yes, and we will explain why today. So there's a nice little quote summarizing a lot of the importance of stellar spectra. A picture is worth 1,000 words, but a spectrum is worth 1,000 pictures. So, as we've already mentioned, and we'll soon discuss in more detail, using the Doppler effect to find how fast stars and galaxies are moving away from Earth is based on the location of various spectral lines. And that's something that we're going to look at today. Spectra are also used to identify the chemical abundances of elements in stellar atmospheres. And, I should mention as a note of historical importance, the element helium, the second most abundant element in the universe, the second element on the periodic table, was actually initially discovered in our sun before it was discovered a few decades later on Earth. And technetium is another element that was discovered in stars before it was manufactured on Earth. The reason technetium does not naturally exist on Earth is because the longest-lived isotope of technetium has a half-life of 1.6 million years. Now, it is created in great abundance during the later stages of the lives of sun-like stars during the asymptotic giant branch. And then after that, it quickly decays. So it's commonly produced in the interstellar nuclear factories, but the reason we don't have it on Earth is, of course, because Earth is a lot older than 1.6 million years. Now, here is a table of some of the most abundant elements in our sun, first by percentage by number of atoms, and then by percentage by mass. And notice that hydrogen and helium are by far the most common. Those were created, after all, during the Big Bang, and our sun is currently fusing hydrogen into helium in its core. And there are also trace quantities of other elements, and how those got there is the subject of a future unit. In fact, it'll be Unit 7. So here is an emission line spectrum. So if you take a gas of hydrogen or helium or sodium or mercury and you ionize it in a glass lamp by passing a current through it, then the light that is produced can be passed through a glass prism, and you'll find that it is composed not of a rainbow, but of certain emission lines. In fact, this line right here at 656 nanometers in hydrogen is a very important line. There's another one right here at 478, another one right here at 435, and another one right here, I think, at about 410. And the combination of those lines times their strengths gives you that nice pinkish glow that you have around star-forming regions that we've discussed before. But notice that different elements have different spectral lines. They are kind of like elemental fingerprints. Also, molecules can have spectral lines as well, something that we'll discuss in a little more detail later. Now, how do you get different types of spectral features? That goes with something called Kirchhoff's laws. Kirchhoff's laws of spectral lines, that is, because those of you who know about electricity and magnetism also know that there are Kirchhoff's laws in electricity and magnetism. But in astronomy, there are really 3 Kirchhoff laws, and they each correspond to a different type of spectrum. So, first, a luminous solid, or for that matter, just a compressed gas, will emit light of all wavelengths, and that will produce a blackbody spectrum. So remember we talked about blackbody spectra in the last video. Blackbody spectra are also sometimes called continuous spectra. And it will, as such, produce a characteristic blackbody curve that has a certain shape corresponding to a certain equation, 2hc squared over lambda to the fifth over e to the hc over lambda kt minus 1, if you plot it versus wavelength. But in any case, it's a curve, it has a mathematical form, and from that mathematical form, you can figure out the temperature of the object just by finding where the peak is, as we discussed in the last PowerPoint video. Now, a rarefied, that is, a diffuse gas, one that is not very dense, but is reasonably energetic, in other words, has a reasonably high temperature, will emit a light whose spectrum shows bright spectral lines. In other words, similar to what you have in this picture. And if you have a black body, where the light from that black body is passed through a cool gas on its way to the observer, then the observer will observe a black body spectrum, but it will have dark spectral lines, like what you saw in the spectrum of our sun. So, those are Kirchhoff's laws. They must be known. You must understand these. Now notice that I said that you must understand these, as opposed to you must memorize these, because we are about to discuss why Kirchhoff's laws are the way they are. So for now, sure, you can memorize them, but the goal of this video is for you to understand why they are the way they are. So first, let's look at types of spectra. Well, here's your continuous spectrum. Here's your situation where you have a black body whose light is passed through a cold cloud of gas. Well, certain lines will be absorbed by this cloud of gas. And then, if you look at the cloud of gas itself from a different angle, very precisely, if it's a cold cloud of gas, cold enough to absorb these lines, then you'll see these emission lines as well. So, can you think of examples of each of the type of spectra in this picture of the Eagle Nebula? In fact, the center part of this is the famous Pillars of Creation, which is one of the most famous astronomical pictures of all time, released by from the Hubble Space Telescope team in the mid-1990s. So, let's see. A black body spectrum would be obtained just by looking directly at any of the stars in this picture, as long as there isn't too much in the way of gas and dust along your line of sight to the star. That would give you a black body spectrum. What about an emission spectrum? Well, an emission spectrum is something that you get from a relatively hot, rarefied gas. Well, that's that pinkish stuff that you see right here. This is glowing hydrogen gas. And by hydrogen gas, astronomers mean atomic hydrogen gas, monatomic hydrogen gas. That's far more common in the interstellar medium than diatomic H2, which is a lot more rare. But it's still out there somewhat, but different than the characteristics of things on Earth. But anyway, yeah, in this hydrogen gas, this is an emission spectrum. That's why it has this characteristic glow. If you were to pass this characteristic pink glow through a spectroscope, you would get pretty strong lines at 656 nanometers, 478 nanometers, 435 nanometers. And you'd also get some helium lines as well, perhaps, depending on whether these central stars are hot enough to ionize helium atoms. What about absorption spectra? Well, how about if you try looking at one of the stars in the center part of this picture through this cloud of gas and dust? In that case, you're going to see a black body spectrum with absorption features. Okay, so why does it work like this? First, we need to talk about atoms. So we're going to take a digression here to talk about atoms. As you know, they're composed of three fundamental particles: protons, neutrons, and electrons, where protons are positively charged, electrons are negatively charged. The protons and neutrons are much, much more massive than the electrons, which means that as the electrons orbit around, the protons can be thought of as really not moving. And the protons and neutrons are contained in the nucleus of the atom. So here we need to also take a little bit of a historical digression to talk about how do we know about the nucleus of the atom. You may have heard about the famous experiment by Ernest Rutherford. Well, actually, it it was not performed by Rutherford, it was performed by his graduate student. Rutherford was not trying to take credit for this experiment. He was already famous. He was trying to help his graduate student become famous, but I guess people saw the line behind the paw print and realized that Rutherford was the one who really came up with the idea for this. But anyway, he suggested to his graduate student that he take a very thin film of gold and shoot alpha particles through it. So how do you shoot alpha particles through anything at all? Well, first you have to make alpha particles. How do you make alpha particles? Well, by the early 1900s, it had been discovered that a number of elements are radioactive, and that some of these radioactive elements emit these things that they called alpha particles. And we now recognize alpha particles to be helium-4 nuclei, but at that time they realized, okay, these things are positively charged, and therefore they can be accelerated in a certain direction by an electric field. So you take a sample of, say, like uranium or thorium or polonium or something like that generates lots of alpha particles, and then you turn on an electric field to essentially collimate and accelerate these alpha particles into your so-called alpha particle gun. So you shoot these alpha particles at your thin foil of gold, and Rutherford suggested that his student have a screen behind the foil of gold to detect the distribution of the deflections of these alpha particles. So, to the student's surprise, there wasn't really any deflection that could be detected. Instead, they all appeared on the phosphorescent screen in the same spot. In other words, just the direction of motion from which they were being shot. Although not quite all of them could be accounted for. Basically, all of them were accounted for, but not quite. So, also, especially based on the fact that they all seem to be going through undeflected, Rutherford suggested a novel improvement to the experiment. He suggested that his graduate student basically wallpaper the entire laboratory with this phosphorescent material that ends up giving a quick glow whenever a charged particle hits it. So the student repeated the experiment, and lo and behold, got the same result, with the exception of the fact that every once in a while another part of the room lit up due to the impact of an alpha particle on this material. And this happened only when the experiment was being done, or at least there was a net difference between when the experiment was being done and when it wasn't. So this seemed very strange. In Rutherford's words, he himself said that it was as if you fired a 15-inch shell at a piece of tissue paper and had it rebound back at you. And that's really what happened here. So this experiment implies two things. One, the vast majority of the atom is empty space. In other words, the vast majority of the alpha particles just pass right through. The second thing it implies is that the positive charge of the atom is all gathered up in a very small part of the atom. And we know that it's a very small part because, again, the vast majority of the materials went through. We know it's positively charged because of the way that they were deflected back. In other words, if it was the negatively charged stuff that was gathered in the middle, you wouldn't have those sharp deflection angles for alpha particles every once in a while. So that was very weird. So all the positive charge is in a very small part of the atom, and in addition, based on the fact that you have these sharp bounce backs and the other types of deflection angles that you had, the conclusion is that this positively charged part of the atom is also very massive, at least quite massive compared with an alpha particle. As we know, a gold nucleus is a lot more massive than a helium-4 nucleus. Okay, so that's how the atomic nucleus was discovered. The neutron hadn't been discovered yet. That was discovered in 1932, but it's bound up in the atomic nucleus. And the strong nuclear force is what binds protons and neutrons together. They exchange quark pairs, actually a quark and an antiquark in the form of pions, but these quarks themselves are more tightly bound by the actual strong force with the gluons and stuff like that. But anyway, the point though is that the atomic nucleus is very, very small, and it is orbited by a much larger cloud of electrons. The way that people can kind of visualize this is that if you visualize an atom as a football field and the surrounding stadium of fans, the surrounding stadium of fans is like the electron cloud. The nucleus, which is where all the mass is, practically speaking, is like a grape seed placed in the middle of the 50-yard line on the football field. So it's like you have all the mass contained in that grape seed and a very tiny part of the mass circling around in a much larger area. So the electron cloud is typically about 100,000 times the size of the atomic nucleus. Now, in terms of the central structure, well, we have the nucleus, which is 2 protons and 2 neutrons, and surrounded by, in this case, the helium-4 atom is 2 protons and 2 neutrons, surrounded by 2 electrons. So there's your structure, and the periodic table is based on the number of protons in the nucleus. It's organized by the number of protons in the nucleus. The mass number is the number of protons plus neutrons. So hydrogen 1 just has a mass number of 1. It's just a proton being orbited by an electron. But helium-4 has a mass number of 4. It's 2 protons plus 2 neutrons, giving you 4 nucleons. The mass number is also called the nucleon number. Nucleons are just protons and neutrons. And then things like silicon has 14 protons in the nucleus, and the most common isotope of it has an atomic mass of 28. So that means that, well, the number of neutrons in that would be 28 minus 14 is 14 neutrons. How about the most common isotope of iron? Iron 56. Well, how many neutrons there? Well, the atomic number is 26, so that's 26 protons. So 56 nucleons minus 26 protons means that it has 30 neutrons. And then some examples of heavier elements, etc. Now, isotopes. Isotopes are situations where you have the same atom, but different numbers of neutrons. So same atomic number, same number of protons, but different numbers of neutrons. So for example, carbon has 2 stable isotopes. The most common is carbon-12, with 6 protons and 6 neutrons. But there's also carbon-13, which is a stable isotope as well. That's 6 protons and 7 neutrons. And as you know, there's another common isotope of carbon, carbon-14, which is radioactive. And it's relatively common because it's constantly being produced by cosmic rays interacting with the nitrogen-14 in our atmosphere. But in any case, yeah, those are 3 common isotopes of carbon. Hydrogen also has different isotopes. The most common form is just a single proton, but there's also deuterium, which is stable. And there's tritium, which is unstable. So tritium being 1 proton and 2 neutrons, so for an atomic mass of 3, hence the tri part. And then other structures of nuclei as well. And as I already mentioned, the nucleus is held together by something called the strong nuclear force, which, other than just mentioning that its existence, need not concern us further for now. Radioactivity. Some nuclei are radioactive, so they can decay from some larger nucleus into a smaller nucleus, or in other cases can actually go from a slightly less massive nucleus to a slightly more massive nucleus, depending on what sort of decay is happening. Although, generally speaking, I think even if you end up going to a higher atomic number, in a lot of cases the mass will end up being a little bit less because of tighter binding energy. But in any case, there's an upper limit for stable nuclei. In fact, quantum mechanics tells us that that upper limit is a mass number of 209, and indeed, bismuth-209 for a long time was considered to be the heaviest stable isotope, because we know that everything after the element bismuth on the periodic table is unstable. In fact, some people kind of say, oh, uranium is stable. No, uranium is not stable. Even the longest-lived isotope of uranium, uranium-238, has a half-life of 4.47 billion years. But now we actually know that even bismuth-209 has a half-life of something around 2 times 10 to the 19 years. So it's very, very, very long-lived, but it's not completely stable. So now we recognize the heaviest stable isotope to actually be lead-208. And lead-208 actually is stable, that is, assuming that protons are stable, which most theoretical physicists figure that the protons will probably turn out to be unstable, but here we'd be talking about half-lives on the order of like 10 to the 34th or 10 to the 35th years. So many, many orders of magnitude higher than this. Now, unfortunately, this discovery of the atomic nucleus leads to a problem with atoms. But it's a problem that will get solved, and the solution to this problem is what leads us to our understanding of Kirchhoff's laws. So, Rutherford used his gold foil experiment, as we mentioned, to note that there's a massive, dense, positively charged nucleus, and this would be orbited by a cloud of electrons. But that's a problem, because if it's being orbited by electrons, electrons are charged particles. And Maxwell's classical electrodynamics that we discussed a little bit before tells us that accelerating charged particles must radiate energy. Well, in the case of an atom, where does that energy come from? It must come from the total energy of the orbit. So if it radiates energy, then the orbit's going to become smaller. And now it's accelerating even quicker, so it's going to radiate even more energy. So, as a result, atoms themselves must be unstable. And it's possible to calculate the typical lifetime of an atom, and when you do that, you get that it's about 1/trillionth of a second. So, therefore, the universe has no stable atoms, and we are not here. So, let's just say that this prediction is not what is observed. But fortunately for us, quantum mechanics comes to our rescue. And it does so in the form of the fact that these electrons in their orbits take the form of waves. So the very fact that the electrons behave like waves means that when they are in an orbit, the shape of the orbit is not what you would call a fixed circle. Instead, the wave is a wavy pattern on the orbit that must meet back up with itself. So, the different types of orbits that it can have depend on the different number of possible nodes in the wave, or the possible antinodes. So, in this case, let me just show you how this might appear. In this situation, I've drawn two kind of diagrams for this in Microsoft Paint, where in the left picture we have an electron in a lower energy level, and thus with fewer antinodes, that is, peaks in the wave, or troughs in the wave, compared with the situation on the right, where in this case the electron is in a higher energy level, and it has more antinodes than does the electron's orbit on the left. But nonetheless, I can still ask the question in each situation, where is the electron? I can't tell you where the electron is. The only thing I can really tell you is where the electron is not. The electron is definitely not at one of the nodes of the orbit. But the whole point is that this wave is vibrating back and forth. So like at the next instant, this part of the wave might be up here, and this part of the wave would be down here, this part would be up here, etc. And it's vibrating back and forth. But these are probability waves of where the electron could be. But it's not in any particular spot until you measure it. But guess what? The only way you can measure it is if you ionize the atom, and then the electron's not going to be there anymore. So, in other words, all you really have is an electron cloud. And because of that, because of the fact that you have this electron cloud, these probability waves of where the electron can be, the only thing you can do to figure out what's going on with the electron's momentum, or its velocity, is to take an average. Well, when you take that average, the direction vectors cancel out. And since the directions cancel out, an electron acting like a wave, therefore, is not accelerating. And since it's not accelerating, it's not radiating. So that is how the picture of quantum mechanics that had already been developed to some extent is able to solve this conundrum of what would otherwise be an unstable atom. Now, the different energy levels are given by the numbers 1, 2, 3, 4, 5, etc. But there is a lowest possible number, 1, because after all, that's the situation where you just have the most basic possible wave. The number 2 is the next most complex wave, the number 3 is the next most complex wave after that. Now also keep in mind that the waves can have different shapes. What I showed in the Microsoft Paint picture was just a 2-dimensional atom. But as you know, atoms are 3-dimensional, and in 3 dimensions these shapes are going to appear differently. In fact, we call them spherical harmonics. But in any case, n equals 1 is the ground state. That's the lowest possible energy. And you can't be in, say, like the n equals 2.5 state, because if you were there, the wave would not meet back up with itself. If you don't have a wave, you don't have an electron. So the electron can only exist in one or another energy level. And the fact that these are energy levels is important, because higher energy levels have higher energies. And therefore, in order for an electron to pass from a lower energy level to a higher energy level, it must absorb energy corresponding to the energy difference between the lower and higher energy levels. And each type of atom, and for that matter, each type of molecule, has a unique set of energy levels. So, as we already mentioned, this does give us the solution to the radiation problem, the fact that these electrons behave like waves, and anything that behaves like waves obeys the uncertainty principle in quantum mechanics, which is derived directly from linear algebra, and it always has to be obeyed. So here is the Bohr model of the atom, where the idea is that in each of these energy levels, the electrons have these wave states in which they exist. Now, what if the electron is in a higher energy level? If it's in a higher energy level, the electron will eventually give up energy. And when it does that, it's going to go down to a lower energy level. Well, the difference in energy levels between the higher energy level and the lower energy level is equal to the energy that was emitted. Well, what is that emitted energy? That's a photon, a particle of light. A particle of light with a specific value of energy, and thus a specific wavelength. I've mentioned that photon that hydrogen often emits that has a wavelength of 656 nanometers. I've mentioned that a number of times in this course. Well, that corresponds to an electron in a hydrogen atom going from n equals 3 down to n equals 2. When it does that, it emits a photon with a wavelength of 656 nanometers. N equals 4 to n equals 2 is 478 nanometers. N equals 5 to n equals 2 is 435 nanometers. Those are all photons in the visible part of the spectrum, and those match the wavelengths that you saw in that diagram that I showed before with the emission lines for hydrogen, though they weren't at exactly the right spots by the measuring tape that was used in the diagram. Incidentally, going from n equals 2 to n equals 1 emits a photon with a wavelength of 121.6 nanometers. That's in the ultraviolet part of the spectrum, so you can't observe that unless you have an ultraviolet observatory. It's a very common wavelength in the universe. It's just that you need an ultraviolet telescope in order to observe it. So that's one of the reasons why we build things like ultraviolet telescopes, so that we can observe these other types of wavelengths out there. And observing them tells us more about the environment in which they were emitted. So, in any case, this is kind of this picture of emission, going from higher energy level to lower energy level by emitting an electron. And, of course, with absorption, that's where you go from a lower energy level to a higher energy level. So these types of actions, emission and absorption, tend to lead to emission spectra and absorption spectra. So, what's going on in the case of absorption? In that case, you have some cloud of generally cooler gas. It needs to be cooler so that the electrons will generally already be in lower energy levels. After all, what do we mean by cooler? By cooler, we usually mean that it has a lower temperature. Well, what does that mean for a gas? It means that the collisions between the molecules are not going to be all that energetic, because the individual molecules don't have all that much kinetic energy. So with a cool cloud of gas, you're more likely to have electrons that are in the lower energy levels. And Therefore, if you place a cool cloud of gas with its electrons in the lower energy levels in front of a black body, therefore you are going to have a lot of absorption taking place as the radiation from the black body kicks those electrons that are in their lower energy levels up to higher energy levels. Well, since the energy ends up doing that, that means the particular energies that had the ability to do that end up getting absorbed. But only the particular energies, at least up to inherent quantum uncertainties and Doppler effects that we're going to talk about later. So, something like this. So yeah, the photon has to have the correct energy corresponding to the energy difference between this energy level and this next energy level. So that's how you get absorption spectra. Now, something that we think of as a cool cloud of gas would be often considered very cool in astronomy. Even the atmospheres of stars are often sufficient to be called cool clouds of gas in astronomy. I mean, I showed the spectrum of the sun before. That was all absorption lines. Well, most of those are caused because of the various elements and compounds that are present in our sun's atmosphere, which, even though it's thousands of kelvins, is still what you could think of as cool on this scale. So a little cartoon of this. If a photon wanders by that does not have an energy corresponding to the energy difference between energy levels for that atom or molecule, it will not get absorbed. Just goes by, it goes on through, it passes through the cloud unabsorbed, and you'll be able to observe it as part of the spectrum. However, if a particular photon comes by with just the right energy level, or just the right energy to cause a transition in energy levels, then you will have that transition occurring, and then it will be spontaneously emitted in some random direction. That's why even when you look at a cool cloud of gas from a random direction, you can often see an emission spectrum from it corresponding to these particular wavelengths that have been absorbed and then emitted in all directions. However, the cloud of gas can't be too dense, because if the cloud of gas is too dense, even if it's hot, well, then this emitted photon will end up either getting absorbed or scattered and bounced around. Well, that absorbing and scattering and bouncing around process for a hot, dense cloud of gas like a star, or for that matter just a warm solid, and it doesn't need to be too warm. For example, I mean, a weasel will work. A weasel is a black body. That's why stars are black bodies, because they're dense enough that any of this emission that happens, it gets bounced around enough that you eventually attain thermal equilibrium, and it just radiates off according to the black body radiation spectrum. So with this in mind, I think that now is actually a good time to conclude this particular video and leave the discussion of the Doppler effect for the next video. So the reason that Kirchhoff's rules work the way they work is because of these different energy levels in atoms. If you have a warm solid or a hot dense gas, then any type of emission will end up getting bounced around inside of the gas or inside of the solid, and things end up balancing out, and you get a continuous spectrum, a blackbody spectrum. However, if you have a hot diffuse gas, well, it's hot, meaning that the kinetic energies of the molecules or atoms tend to be pretty high. So they whack into each other with high energies, and the energies, the kinetic energies of these collisions can be used to transfer electrons from lower energy levels to higher energy levels. In fact, exactly how that occurs is something called the Boltzmann equation. Now, as a result of this, a hot diffuse gas therefore will have atoms and molecules that have electrons in higher energy levels, which means they are going to be more likely to spontaneously emit radiation. And therefore you're going to see you're going to see emission. You'll see emission lines from these hot diffuse gases, which are more likely to have their electrons in excited energy levels, higher energy levels. However, with a black body, that's all going to get absorbed again, scattered about, averaged out, and you just get a continuous spectrum instead of strong emission lines at particular wavelengths. However, if you take that black body spectrum and pass that light through a cold cloud of gas, well, cold cloud of gas, those molecules don't have enough kinetic energy to really transfer into all that much in the way of higher energy levels for those atoms and molecules. So in order to make atomic transitions, they need to absorb light from outside sources. Well, how about a black body that happens to have its light passing through the cloud of gas? In that case, there will be absorption of photons corresponding to the particular energies that are the energy differences between these lower energy levels that the atoms are already in and the higher energy levels that they can potentially be in. So some photons will get absorbed, the ones that have those particular values of energy. Others will not. So that's kind of a summary of the spectral features and why you have spectral features, how that comes down to atoms, and how those energy levels end up coming back together to give us a picture of why Kirchhoff's rules work the way they do. So, hope that was helpful to everybody, and thank you for watching, and I'll see you next time when we discuss the Doppler effect.